Hello, everyone, and thank you for joining our presentation today. My name is Chad Gillespie with Mitsubishi Electric. I'll be talking about applying ducted and split ductless systems in high-performance homes. We also will have Kimberly Llewellyn, who is also on the performance construction team for Mitsubishi Electric, and she will be giving the second part of the presentation. And a background on what we do. We are a manufacturer. Mitsubishi is a manufacturer of high-performance HVAC systems. You might have seen our mini splits and our ducted systems in many high-performance homes. And today we really want to give you a little background, since there's been a lot of discussion about using our products in traditional homes, high-performance homes, tiny homes, and we want to give everyone just a little bit of background on what we recommend as far as designing with these. Today will be a very high-level presentation. There's a lot that goes into designing with any product, whether it's ours or any other HVAC product, and we want to really just talk about some of the highlights of what you should consider. We do offer more in-depth presentations on design with our products. We can do those locally. Is up to 1 hour presentations, up to 3 hour presentations on design. So with that, we'll start. And again, we have myself and Kimberly Llewellyn. And Kimberly Llewellyn has a background in engineering, and she is on our team for performance construction, which focuses on newer high-performance net zero passive houses. She is really our technical lead. So when I get through some of the background of what a high-performance home is, we'll pass it off to Kimberly so she can give you some of the details of what she sees as important for designing with high-performance homes. So some of the objectives that we want to talk about today, really the basics, describing the characteristics, requirements of what we consider a high-performance home. Today, we see lots of variations of high performance. Anything that's really above the standard building code, we like to call high performance. That could be, an Energy Star home. That could be a passive house. That could be a totally net zero house. And there's lots of regional programs. So we'll talk a little bit about some of those different programs and what we think is considered high performance. And again, how to achieve the best performance using our equipment. There's lots of things to consider, lots of styles of our products, lots of regions that we deal with around the United States that all add into very specific designs to make sure that you have a high performance home. Again, with the methods and again, the advantages. Some of the advantages of using our products we'll go through. There's many of them. And we really think that they are really starting to fit in well with today's new and advanced homes. So the first thing we do is when we design for homes, we really set out to the three main goals that we look at for high performance homes when we're designing for these. And really we talk about comfort, health, and energy efficiency. And those are really our three principles that we follow. We really kind of add in a fourth is durability, but that's underlying to all the main 3 points of comfort, health, and efficiency. And it's really important. So many people focus on energy efficiency, and that is a main goal of a high performance home, but we really don't want to forget the comfort of the home, and health is extremely important. As we look in today's homes, the tighter they get, the more important it is that we have the proper ventilation for the home, and that all the occupants are getting fresh air, and we're removing any types of air pollutants from outside or that are produced inside. So that's why it's really important that we get these designs right. And most of the time we're going to need fresh air or some type of fresh air integration with our products. And when we describe high performance homes, there's lots of ways to do it. I mean, these are just some of the parts of a home that we discuss as high performance. You'll certainly see different techniques. Some like to have extremely thick walls, double stud walls, outboard insulation. Some like really high upgraded windows. Some like to use high performance HVAC systems. So they really all should be part of the equation when you're building a home. And depending on what market you're in, sometimes added insulation is not always the best. Sometimes it could be better windows depending on the orientation of the house. So really we have lots of components that go into the design of the home. And again, we could spend 2 hours just talking about an overview of the types of components. But today we're really just going to try to focus on how HVAC, especially with our products, mini splits and ducted mini splits, fit into that equation. And again, one of the biggest things that we see is with these components, we see the need for lower loads, or we see the result is lower HVAC loads in the home. And you really want to design your home with an accurate load calculation and not be oversized. Kimberly will go through some of the expectations of loads and how they've changed over the last 20 to 30 years, and why traditional equipment will not fit in all of today's homes, especially the very tight, efficient, upgraded homes, passive homes, net zero homes. So just to kind of give a little background on, a brief background on the statistics and trends, high performance homes are not really, small, tiny homes or the very rare passive house. We're seeing lots of changes, not only in codes, but adoption from local states and localities on upgrades in energy efficiency, what we call strategic electrification. And that is just trying to remove as many fossil fuels from the grid as possible. So we're seeing a lot of that pushing into the traditional housing market. With that, we get a lot more heat pumps that are being expected to be used, and again, much more efficient products than what has traditionally been used. And in some areas that you may or may not have heard, California is looking to go every residential home to be built by the year 2020 will be net zero. Every commercial building by 2030 will be net zero in California. And you'll start to see these codes move up the West Coast, Oregon, into Washington State, of moving into strategic electrification, reducing their carbon usage, and again, that really kind of lends itself to high performance HVAC, heat pumps especially. So a lot of things are changing, and again, it starts on the coast, the West Coast, and really goes over to Massachusetts and New York, and those codes really get adopted and move down through the East Coast. So there's a lot of momentum with this. Other areas like Denver and Boulder are very big supporters, Austin. So these are just a handful of cities that we deal with that are moving towards a higher performing home. And with that, we have to adjust our systems. And today we look at homes that, almost 30 to 35% of new construction homes are considered higher performing or above code. So with that, there's lots of opportunities for us to grow our product. So as I discuss codes, you can see the more stringent energy usage or the reduction that they see in this code cycle. And really what this graph describes is the code and the efficiency. And really from 2006 to 2012 was the biggest change in what expectations were for energy usage in homes. 2015 and 18, subtle changes, but we will continue to see more advancements in the code further on to even get to net zero by the next 20 to 30 years. So that is the ultimate goal, is to get to net zero. But as you can see here, the codes are driving that. There are certainly many things to consider with the environment and electrification. And again, we want to be part of that. Now, some of the groups that we work with and that have their own regional programs, we can see some here on the screen. We deal with Earth Advantage out in Oregon. They really have their own code design for high performance homes. And you can see Energy Star, which has been around for a long time. And then followed up with that, the Zero Energy Ready Home. Sam Rashkin is part of both of those and really instituted this program, which is a great way to get to zero. But it doesn't mandate that you have to put solar in your house. You just want to get to a point that you are extremely energy efficient, and then if you ever adopted a renewable source, that you could get to zero. And of course, FIAS Passive House, that's an extremely great way to build, very tight, very, very low load. And again, we are a big part of all those construction techniques. And if you're building a passive house or a net zero ready home, we certainly can be part of that. And we do quite a bit with all these organizations. And this next slide is really, how do we measure? What is the easiest way to measure the actual performance of the home? Most people that are working in high performance construction understand the HERS score. And really, this is just a gas gauge for your house. So it's the lower the score, the better. And here we can see that you have the HERS score. 100 is the baseline based upon a 2006 code built house. And then you can see the score as it slowly drops to Energy Star, Passive Home, and Net Zero homes. And really, our goal is to try to help lower scores. And this is for the builder as a direct reflection of how well this house performs. So homeowners can now purchase a house and see with this HERS rating exactly where this house that they're buying compares to another builder's house. And it does a really great job of showing where the rating and the performance of the home is. But again, the ultimate goal for one day is to get to net zero, and that is that the house produces as much energy as it consumes. Next slide is just showing that for people to understand that net zero is not terribly expensive. Most people have this idea that if you try to get your house to net zero, that it's it's a $75,000 upgrade. It's super expensive. In a lot of cases, it's certainly not. This graph represents just the overall ownership per year of a home with a traditional mortgage, and then if you had net zero with your utility costs built in. And you can see over a year that the cost is consistent for net zero, and that it actually is cheaper to own a home built to the standard here versus a traditional house having it be net zero. So it's really the ultimate goal is to get to zero. We use net zero in luxury homes, of course, average construction income level, I should say, as well as affordable housing. And the goal is for affordable housing, like Habitat for Humanity, is to be able to provide a home that is sustainable, durable, and affordable. And so when the homeowners buy the home, that they can afford to live there. And that's what a big part of getting to zero is so important. It provides housing for all. So with that, I am going to pass the screen over to Kimberly Llewellyn, and she's going to discuss more of the design considerations that we look at when we're designing homes.
Thanks, Chad. So I'm picking up here with design considerations, and we're going to get into some of the details about load calculations and ventilation loads, equipment selection. And really, as an industry, we're having to talk about this more because we haven't been too used to considering HVAC systems a whole lot. It was just something that got done as part of the construction process, but it'd been working fine enough for decades. But because our buildings are changing as quickly as they are, as Chad pointed out with that code change graph, where we saw that we have a reduction of almost 50% of our energy use in buildings mandated by code, because we're going through that kind of change. There are some concepts that we have to get into what I call our working knowledge as an industry, so that we know how to look for, consider, and work some new things into our construction process. So some of those are the following, what we have listed here: proper load calculations, sensible heat ratios, and I'm going to do my best not to lose anyone on that, latent loads and ventilation latent loads, and equipment selection. So really all of those have something to do with load calculation. So we're going to start there. So a load calculation, just to make sure we're all on the same page and we all understand the concept. A load calculation is something that's used to predict what the peak heating and cooling needs of a building are. And the industry best practice is an ACCA Manual J. And so a lot of times you'll hear people refer to load calculations just as a Manual J, because that's really what most people do. And there are a number of inputs that go into a Manual J, which is really just a calculation method or an energy model. And some of them are obvious, and some of them might not be quite as obvious. So some of the ones that seem really obvious are, okay, well, you got to put a project in its proper location. So climate, that's where you get your climate information from. And then you also have to put in all of the details about the actual construction type of the building. So what are your wall assemblies like? What kind of insulation, sheathing even? How many windows do you have and where are they? What direction are they facing? where are your mechanical systems located, what are your internal loads, and we won't go too much into that, but maybe a little in a slide from now. So some of these inputs have more impact than others, and I'm going to point out to you just a few that are most impactful, because my goal here is to give builders, in particular, in this forum, a sort of takeaway list of, 2 or 3 things that they know by the end of this that they don't know now. Like, what do I need to look for, and how important is it? So it's really critical for a project team in general, not just the HVAC contractor, but the builder and the architect, to understand what the impacts of loads are, so that when changes happen, and they always do happen, whether that's on a plan set or in design phase, or if that's in the field. Some things that happen, some changes that happen, have more of an impact than others. And we need to make sure that they get communicated either to the mechanical designer who's doing the load calculation, or the HVAC contractor who's doing the load calculation and the installation. So this is just a snippet of a load, what's called a load preview report, where we summarize all of the various loads of different rooms and zones of a house. And what I've done here is show you, we've got the exact same building here. So if you look at the area, which is the square footage that we're considering here in this load calculation, 3302 and for the top and 3302 for the bottom, that's just showing you this is the exact same building, and all we've done is rotated that building 90 degrees. And that rotation in 90 degrees has made a 2-ton difference in the cooling load. So if I give you a top 2 or 3 takeaway list, after getting a project in the right place for a load calculation, getting the orientation for that building correct can be critically important, especially if a building has a lot of glass in it. And that tends to be, we're seeing that as an architectural trend currently, where we've got a lot of glass, and people wanting to feel like they're bringing the outdoors indoors. So when you have a wall of glass, getting that orientation and that square footage of the glass can be very, very important. So another thing that's critically important is to make sure that you have what we call a room by room load calculation. So if you remember in that previous slide, there were different lines that had actually different rooms called out. If you don't see that in a load report, and I should mention that builders should be asking for load reports from their HVAC contractors or designers. It's something that nobody would expect you to pore over, but you should certainly, I'd like to encourage you to get familiar with them and to know how to review these key points. So that line item with each individual room will show you that you actually have this room by room load versus a block load, which would be an entire load for a whole home. And the reason that we want a room by room load is because that's what tells us how much air needs to be delivered to each room. So, or how much capacity, they're directly tied, the capacity and the CFMs, how much capacity each room requires. If we don't do that, we can't, we can talk about zoning all we like, but it doesn't really make sense. We'll be more or less guessing about what the real needs of those individual spaces are. So now we're gonna talk a little bit about what's called a sensible heat ratio. And this is really important because, like we've been saying, like the load profile, the energy usage of our buildings has been changing fairly drastically over the last 5 code cycles. And so what we have seen as a result of paying a lot of attention to the requirements we make of our building envelopes. So by that, I just mean insulation, infiltration, glass specifications. As a result, our sensible loads, our heat loads, have drastically decreased. So whether we're talking about heating or we're talking about cooling, we're in heating season, we're not getting the losses that we would normally get in spaces because our building envelopes are performing better. We don't have as many conductive losses or infiltration losses through our building envelope. And in cooling, we're not getting the gains because our glass specification has gotten better. And again, because our building envelopes are performing better and we're not having the conduction losses that we had prior. But what's not changing are what we call our latent loads. So latent load is just another way to say moisture load or humidity load. So if we consider, a way to describe what is changed about spaces as our codes have increased and building performance has improved, the sensible load has gone down. The latent load has stayed the same or even increased due to ventilation requirements. And so what we call a sensible heat ratio, which is really just a simple fraction of sensible heat or sensible load over our total load, that number has gone down. Now, some of our higher performing equipment, the SHF or sensible heat fraction, which is really the same thing, has gone up. So we have to make sure that we're tracking the sensible heat ratio of spaces and the sensible heat fraction ratio of equipment in order to make sure that we are specifying equipment that truly meets the needs of these spaces. So I want to break down here the issue of latent loads and ventilation requirements so that we can really look at it specifically. What are the challenges when we start being compliant with ventilation requirements? So I've picked Atlanta, Georgia here. That's where our Mitsubishi headquarters are located for HVAC. And I'm going to go slowly here because I want to make sure I don't lose anyone. I think this is maybe the most important HVAC topic of the day. So what I've done here is we're looking at psychrometric weather data. All that means is that we're looking at weather data for Atlanta, Georgia, and we're considering the number of hours out of the year when we fall into the following weather bin. When we are in a dry bulb range between 55 degrees Fahrenheit and 80 degrees Fahrenheit, which is what we also call shoulder seasons, or some people call it floating seasons. But basically, these are the hours out of the year when you're not going to get a whole lot of assistance from an AC or HVAC system, from a heat pump system, because it's just not having to work hard enough, especially not with higher performing homes. You don't have enough gains to get that system on and running continuously for long enough to remove significant amounts of moisture from the air inside your home. So we're looking at that dry bulb, what we call dry bulb band. And then we're also looking at the conditions that where we have more humidity outside, humidity ratio. So that humidity ratio you'll see we've called humidity ratio has a units of grains per pound. And again, don't let your eyes cross here. It's just an amount of water. And so for reference here, our design conditions of 75 degrees indoor and 50% relative humidity equates to 65 grains per pound. So what I'm looking at here are humidity conditions that are above that 65 grain per pound, because again, we're considering ventilation loads. So that means if we're bringing outside air in and it has more moisture than what we want inside, then that's going to be an additional load that we have to consider. So you see this 8760 at the bottom left of the screen. That's the number of hours out of the year. And for Atlanta, Georgia, we have 2,900 hours out of the year that fall into that described weather bin. So that fall into that temperature range between 55 and 80 and that humidity amount above 65 grains per pound. So that's a huge number out of the year. So in fact, it's just around 30%, 33%. So we're talking 1 out of every 3 hours in Atlanta, Georgia. If we're ventilating continuously, that's a load that we've got to consider. So now we're going to look at some of the ways we can apply variable capacity heat pumps to higher performing homes. And we'll also talk briefly about how the systems work, what makes them variable. So most people think of mini splits as being just ductless, but as you can see here, we have a variety of products that are available in our residential lineup. On the upper left-hand side, we've got multi-position air handlers that have a very similar form factor to traditional air handlers and furnaces. We also have a host of several ceiling mounted options, 4-way cassettes, 1-way cassette. We have a floor mounted option, which is really a low wall mounted option, along with all of these wall mounted options that most people think of when they think mini split. And then we also have horizontal ducted or compact ducted units, which are particularly popular when we have space constraints or an objective to get all of your mechanical systems and ductwork into conditioned space where you might have something like a vented attic. There are a variety of controls that are available, including options to integrate auxiliary systems like ventilation units, dehumidification units, or auxiliary heat systems. All of that can be controlled remotely through phone apps. So because of the slim profile of our outdoor units, we have a mounting option where you can actually put one of the outdoor units on an exterior wall, which is in fact the most common application that you see if you go to Asia or Central America. Often we'll see them actually up on the exterior walls of buildings. Additionally, the outdoor units are very quiet. So for infill projects where you might have smaller, closer lot lines, the quietness of the operation of the outdoor units is a huge advantage. One of the most exciting products that we have just released to market this year is a 1-way ceiling cassette. It's one of the products that allows us to separate out something like a great room, like you see here, a living, probably dining and kitchen room area, separated out onto its own zone so that the comfort of that one space can be controlled completely independently from the rest of the house. So we're going to talk just for a second here about how our systems operate and why variable capacity heat pumps in this current building market where we've got, much lower load homes. So on a real high level, conventional equipment just doesn't come small enough to actually meet the load needs of higher performing buildings, whereas variable capacity heat pumps come as low as 6,000 BTUH or half a ton cooling capacity. So that really is a better fit for a lot of these really low load homes. Another thing that the variable capacity equipment can do that conventional equipment cannot is that, as communicated through the name, it allows the system to vary the capacity that it's delivering to the inside of your house. And What that means is that you're only using as much energy as the house requires, because remember we said with the load calculations, the load calculation is characterizing the peak needs of your house, but you're usually not seeing those kinds of peak conditions. In fact, you're only seeing that about 1% out of the year. That is in fact how we design those. That is in fact how we do a manual J. We use the 1% design condition. And so all the other hours we're seeing something less than that peak load. So we want to have a system that can in fact just deliver as much capacity and so use just as much energy as we actually require. It's also because of by nature of being able to ramp up to the compressor speed that we need to be operating at, and to be able to sort of hover around those interior set points. You might think that that's harder on a system because it's meant to be operating almost continuously. But in fact, anyone who knows motors understands that it's that startup that's hardest on a machine. So, so by virtue of just hovering around a set point and not going on and off the way that conventional systems typically operate, it's actually much easier on the system. So that means that we have more longevity and durability of variable capacity equipment. As I sort of mentioned before, like with that great room scenario, you also are able to truly zone a house according to space use and maybe load profile. So you see on the slide here, we've got a great room, which is a very common, design currently, where you might want to separate out that zone from, say, bedrooms or an office space. And especially with our multi-zone systems, you're able to connect different interior spaces, have them operate separately and independently comfort-wise, but connect them all to the same outdoor unit. Here's an example of one of our designer series wall-mounted units being used in a great room, living, dining, kitchen area. It's a very common application that we see. And, it's worth pointing out that our wall-mounted units, sometimes we get pushed back on the aesthetics, but there really are a lot more options than people are aware of. In addition to a designer series and that other product that I showed that mounts up into the ceiling, we also have a number of contractors that do finishes on these that completely make these systems disappear into walls. You could put wood grains or any other color onto these. So now we'll look at a couple of just actual designs, examples of designs that we see very frequently. Some of the advantages of these designs are that when we're able to separate out different zones, we've increased the potential for health, efficiency, and durability. And on the health front, by reducing ductwork, by taking a zone like a first floor off of one centrally ducted air handler, we're able to greatly reduce the amount of ductwork in that house. And we know that less ductwork is generally better, in part because the systems in general are seeing less pressures in the duct systems. That means that less chance of pulling in contaminants into the duct system and dispersing them throughout the home. It also allows us to more efficiently use the air that we're pushing through these systems. I pointed out those gray boxes that look an awful lot like our typical conventional furnace air handlers, and we call those our ducted multi-position air handlers. So So in the case of a retrofit, or maybe a bottom floor of a 2-story house, we'll often see these located in a mechanical closet with some sort of central return and then distributed supply air. And this slide also just points out the basic elements here of a completely connected system, which include the indoor and outdoor units, the refrigerant line sets, the ductwork, and most importantly, I'm breaking this down to call attention to the controllers, because sometimes we don't talk about controls soon enough in the process, and it's definitely worth finding out what your homeowner expectations are for controls, maybe remote accessibility, wireless or not wireless. And then we have our concealed horizontal ducted units, which get called a bunch of different things. Some people call them pancake units because they're more flat. We also call them compact ducted units. So we're talking about the same thing no matter what we're calling them there. But like I mentioned before, they're really useful if you've got, say, a vented attic and you want to get all of your mechanical systems into conditioned space, because that is one thing I didn't call out earlier in the load calculation portion, but getting your mechanical systems into conditioned space can easily take a ton or 2 tons off of a cooling load, depending on where your project is located. So just getting it out of the attic and into, inside your thermal and air control layers can have a huge impact on that load. So we see this a lot, especially in high performance homes, where these units will be located in the ceiling of a closet or in a soffit drop down in a hallway. And then we see, so this here looks like they've got it in a closet, and then they're running supply ducts here to individual rooms and different spaces. In this case, this is showing 2 compact ducted unit, 3 actually compact ducted units, line sets going to the outdoor unit, and then independent ducting for each of those indoor units. And more frequently, we'll actually see some form of a hybrid design where we'll see that we've got a ducted unit for maybe a cluster of bedrooms, and then we'll have a ductless unit here in this sort of living kitchen area, like I've been pointing out, and then maybe another ducted unit over here. This is showing ductwork, but I want to make sure that we cover this application because we see this so frequently that maybe in a modest 2,000, 1,800 square foot house that's got a great room on the bottom floor and bedrooms upstairs, it's very common to see a ductless unit downstairs serving that big room, and then a ducted unit serving bedrooms upstairs. So one of the advantages to ducted systems is that it allows you to integrate a ventilation system or a dehumidification system. And that's important sometimes because some projects don't have the space or the inclination to have 2 independent duct systems, and we want to make sure that our ventilation air is in fact distributed. So one of the programs that Chad pointed out, FEIS, actually has a requirement that you get ventilation air to the bedrooms. And so it wouldn't cut it to just dump that ventilation air into a central location. It's really important that we actually get it into the air distribution system that exists, sort of like what you see here on the screen, so that it can get out to all of the bedrooms, or you're going to have to run an independent system. And we do both. I mean, sometimes the only duct system is the ventilation system because we have ductless everywhere else. But in the case of where you have ducted units and you have an existing air distribution system, it allows you to integrate like this. If that looks complicated, it is, and it's really important if your space is small to actually, maybe not do this this detailed design, but this does call your attention to the fact that ducts really take up space, and it's not magic. We can't do it by magic. So you got to make sure that if you're trying to get a lot of equipment and ductwork into a particular space, you might want to go measure it out. And controls, I pointed it out earlier that controls are really important to bring up with homeowners and designers. They'll oftentimes get left to the end, but occasionally, the controls and then the chosen equipment may not match. So it's really important to talk upfront with your occupants and your designers about what the expectations there are for not just controllability, like is a handheld remote okay, or do we need to talk about another option, but also remote accessibility. Do we need to make sure that we set you up with a system that you can access from your phone wherever you are? So with that, I'm going to hand it back over to Chad.
Thank you, Kimberly. So now we'll go over just a couple of examples to show some of the designs that Kimberly just spoke about. The first one is a small house that one of our team members did, and we called it the Drift House. And it's a smaller home, and we wanted to put this in here just to talk about some of the design concepts that Kimberly just mentioned. This house uses only ductless wall-mounted units, and it does use an ERV to move the air around the house. And so this is a concept that has been utilized a lot recently. And so we want to briefly talk about how that works. So normally, if we're using wall hungs, if we were to put one in every bedroom of a newer above code house, we would be way oversized. Even though our systems do ramp down, there is still a minimum that they can ramp down to. So sometimes in these higher performing houses, we'll put 2 or maybe 3 wall hung units in, and because the house requires ventilation, we'll use the ERV to help distribute the air around the house. So this is not it's not completely simple. It has been done many times, and it is certainly effective, but it is definitely a way to get specific comfort in those main rooms, and then also use the air distribution strategy to get air into the other rooms. So again, smaller house, 3 wall hungs, and a ERV. Now this next residence is similar, and what we have here is, if you can see, as Kimberly was talking, the horizontal ducted units. And this concept that we have has the dark black box that you see, the square in the middle, is the ducted unit. The GE09 is a wall hung, and then you have a transfer fan. And so what we have here is the main ducted system is handling the office down through the kitchen and the great room. So that's one zone. And then here you have the master bedroom that's handled by one wall hung. So if they want to turn down the rest of the house at night to save energy, and then just use this one wall hung to heat and cool the bedroom, they can. Now the transfer fan is used to take air into the master bath, and that way they can get air into the bathroom. And then there was used a continuous bath fan to help exhaust the air out. So again, you can use multiple strategies with our units. So again, here we have a ducted unit to handle most of the house, and then you have the wall hung that handles the bathroom and the master suite. So again, we can do a lot of different things in our specific design training that we can conduct. We go a lot more into details in the considerations of what size transfer fans or supplemental fans or bath fans in conjunction with our units. So today is just a brief overview of what we can do. Now to go to something completely the opposite direction, there is a home that we did called the New American Home in Florida, and we did this with the IBS International Builder Show. And this is an amazing home, and you can see it's larger than the previous homes. But we wanted to show you an example of some of the houses that we do that are on the luxury end, and this is certainly one of those homes. It uses multiple systems. You can see the different products on the right-hand side of the screen. So it's a conjunction of not only ducted products, but also one of our cassettes, and then some of the wall-hung units. So again, this house it was really important for the builder to use our products for several reasons. They wanted to be able to zone the house for comfort, and they have some different types of spaces. It has a very large living area that faces the back of the house that has sliding doors that all collapse into the wall, and so it opens up. And So sometimes they may open that up and then they'll close it, and then they've just now introduced a month of cool air or warmer air than they wanted. So they wanted to be able to ramp that system up to bring it back down to the set point they looked at. If they didn't have this zone system, then they would possibly most likely overheat or overcool the other rooms if they were on the same system. So this house really delivered what the builder was looking for. Zoned systems, extremely quiet, very efficient. And as Kimberly mentioned, the outdoor units are extremely quiet. And so one of the biggest things that they really liked about this is the outdoor living space really takes up the whole backyard. And our units had to go somewhere, and they were close to the backyard, but they're so quiet that the builder said he's never had a unit anywhere like this, and this has by far been his best living space, outdoor living space. So there's lots of benefits to the system. Again, very quiet, outdoor units very quiet, the indoor units very quiet. This house, because it has multiple systems, it has multiple points of filtration. So again, you're not introducing air that came from the kitchen to another bedroom. So these zones are built independently, and then it uses a completely separate dehumidification system to dehumidify this house. So it's a really unique strategy in the fact for what these luxury builders have been using in the past. He is only going to move forward using this product. And again, we're starting to use a lot more of these in the luxury homes. Builders are looking for equipment that lasts longer, that is extremely quiet and performs well. As Kimberly said, with our compressors, the way they work, they're built to last. They don't have that cycling on and off that really wears down a unit. Ours are built, we expect 20 plus years out of our units versus the standard HVAC systems are about 12 to 14 years. And here you can just see how the zones are broken up. This is a great infographic for one of our marketing team members put together, and it really just shows how the zones are broken up. That main room to the zone 3, those are the doors you'll see that open up to the outdoor living space in the rear. So again, they needed some zoning capabilities so they would not have to really ramp up that system and worry about overcooling or overheating the other rooms. And so to really finish this off, we wanted to talk, because this is can be such a complex topic, we wanted to just give an overview of what was possible with our products and the benefits of our products. But Mitsubishi Electric has been providing top-level service and training for contractors, distributors for years. And we have over 4,000 diamond contractors that are in the U.S. Today that can support installations of our products. But what we've done more recently is integrated builder training, specific high-performance architect training for high-performance homes, HERS Rater trainings. So we can do a lot to help on the specific design and the very critical parts that Kimberly briefly got into on the design portion. As we move forward, a simple application that an HVAC installer might recommend, which used to be for every 400 square feet of area, you use 1 ton of conditioning. Well, that today we can do 1,200 square feet with 1 ton of conditioning or even more. So that really doesn't work anymore. So we have to be very specific and make sure we have a good design, and then we'll get optimal efficiency, optimal air quality and health, and again, a product that lasts. And then further is what we call our zone comfort solutions. That is all of our products and how we design and market our products. You get the comfort part of it. And that is really the most important thing that we've really talked with homeowners, is having that comfort for themselves and for their family. And that will be the end of the webinar today. We do have time for questions, and we'd like to open the floor if we have that ready to go.